Hello friends, welcome to this lecture. In this lecture we will continue our discussion of finding Frobenius series solution method for linear ordinary differential equation having a regular singular point. So, what we have seen in previous lecture that we are considering this equation that y double dash t plus p t y dash plus q t y equal to 0 here, and here we are assuming that t equal to 0 is a regular singular point. It means that it is a singular point. It means that pt and qt is not having a Taylor series expansion, but tpt and t square qt is having a power series solution, power series expansion like this. Tpt is written as summation n equal to 0 to infinity p n t to the power n, and t square qt is having power series expansion as n equal to 0 to infinity q n t to the power n. And here we have seen that in this case we may try our solution like yt equal to n equal to 0 to infinity a n t to the power n plus r, and using this series solution we have just calculated that if you plug in this value, then we have t to the power r minus 2 into n equal to 0 to infinity a n f of r plus n plus k equal to 0 to n minus 1 q n minus k plus r plus k p n minus k a k into t to the power n here. Here f of r plus f of r is defined like this. F of r is a quadratic equation in terms of r, which given as r into r minus 1 plus r p naught plus q naught, where p naught and q naught is coefficient here. So, using this expression we have this following term, and this is the coefficient of t to the power n. So, here equating the coefficient of t to the power n to 0, we have this expression that a n f of r plus n equal to minus k equal to 0 to n minus 1 q k plus r plus k p n minus k into a k. So, here using this formula we can find out the coefficient of a n depending on r and the previous coefficient a naught to a n minus 1. So, here we have considered several cases that here there are possibilities that here r 1 and r 2 are roots of f of r such that r 1 is greater than or equal to r 2. So, here one possibility is that when r 1 equal to r 2, that we cannot use this formula to find out the second solution, and another possibility where we are not able to find out the second solution is that case when r 1 minus r 2 is some kind of integer. In that case also we are not able to utilize this formula, because this f of r plus n is going to be 0 for when we are considering the lower value that is r 2 here. So, the case when we can use this formula to obtain two Frobenius series solution method is the case when r 1 and r 2 are not equal and r 1 minus r 2 is also not equal to any kind of integer, and in this case we can find out two Frobenius series solution method. And let us find out the example where we can have this possible case. So, here we are considering this case. So, we are considering following Bessel's equation of order p. So, here we need to find out two solutions of Bessel's equation of order p, where Bessel equation is defined as t square d2y by dt square plus t dy by dt plus t square minus p square y equal to 0, where t is greater than 0. So, first thing we have to look at that t equal to 0 is a singular point. So, if you look at the coefficient of highest order derivative present here, that is d2y by dt square, if you look at the coefficient is t square, and coefficient of t square means that at t equal to 0 this t square is equal to 0. So, it is a singular point of this equation. And how to check that it is a regular singular point? For that you divide by t square and look at the coefficient of dy by dt here coefficient. So, it means that when you divide by t square, it is reduced to d2y by dt square plus 1 by t dy by dt plus t square minus p square divided by t square y equal to 0. So, here it is your pt and it is your kt. So, tpt is what? Tpt is equal to 1 here. So, this is we say that it is analytic. Similarly, you can look at t square qt, that is t square qt is equal to t square minus p square here. So, here this is also a having a series suspension, or we can say that TPT and T square QT both are analytic. And in fact here your this series suspension have only one term, that is P naught, that is equal to 1, and here we have two term in suspension of T square QT, and here Q naught is equal to minus P square. So here we can say that since T equal to 0 is a regular singular point, as Pt equal to 1 by T and Qt equal to 1 by T square minus P square are not continuous at T equal to 0. So this is another way to check that a given point is a singular point or not. So here you have to check that Pt and Qt are not continuous function at T equal to 0. So in this way also we can check that T equal to 0 is a singular point. Now T equal to 0 is a regular singular point, as both Tpt and T square Qt are analytical function. So here Tpt is 1 and T square Qt is T square minus P square, and both are analytical function, or we can say that both are having Taylor series suspension here near T equal to 0. So it means that it satisfies the condition which we have discussed earlier, that T equal to 0 is a singular point and T equal to 0 is a regular singular point. So here assuming that yt equal to n equal to 0 to infinity a n t to power n plus r is a solution of this, and then we try to find out the coefficients a n and the possible values of r for which it act as a solution here. So again do it in a same way, you calculate y dash t equal to n equal to 0 to infinity n plus r a n t to power n plus r minus 1, and calculate y double dash t, that is n equal to 0 to infinity n plus r minus 1 a n t to power n plus r minus 2. So we can write Ly as n equal to 0 to infinity n plus r minus 1 a n t to power n plus r plus n equal to 0 to infinity n plus r a n t to power n plus r, this corresponding to Pty dash, and here it is Qty, that is summation n equal to 0 to infinity a n t to power n plus r minus n plus r plus 2 minus P square n equal to 0 to infinity a n t to power n plus r, and that is equal to 0 here. So here we can write this is as n equal to 0 to infinity, we just collect the term of t to power n plus r and t to power n plus r plus 2. So here we write n plus r minus 1 plus n plus r, so here this term plus this term plus this term. So when we calculate, it is n plus r into n plus r minus 1 plus n plus r minus P square a n t to power n plus r. What is left is this, that n equal to 0 to infinity a n t to power n plus r plus 2, that is written here. So Ly is given as this. So once we calculate Ly, then we can say that solution y is a solution of this, provided that this quantity is equal to 0. So we need to find out that this expression has to be 0. So equate the corresponding term of t to power n to 0 here. So first look at the coefficient of t to power 0 is equal to 0, and if you look at the coefficient of t to power 0 is equal to 0, we have this here you will get the lowest degree term is t to power r here. So t to power r you will get when you put n equal to 0 here. So when you put n equal to 0 here, we have r into r minus 1 plus r minus p square into a0. So that we are writing f of r a naught equal to 0, that is r into r minus 1 plus r minus p square a naught equal to 0. So if you simplify, this is what r into r minus 1, that is r square minus r plus r minus p square. So it is written as r square minus p square a naught equal to 0. So that is corresponding to equating the coefficient of t to power 0. So equating the coefficient of t to power 0, we have r square minus p square a naught equal to 0. Similarly, you look at the coefficient of t to power 1, and this we will get from this. So here when you put in n equal to 1, then we will get the coefficient of t to power r plus 1, that is r plus 1 plus r plus 1 into r plus 1 plus r minus p square, which we call as f of r plus 1. So here f of r plus 1 is given as a1 equal to 1 plus r into 1 plus r into r plus 1 plus r minus p square into a1. We will not get any contribution from this term, because here n is starting from 2 here. So here if you look at, here we are looking at this is r plus 1, and here it is t to power r plus n. So, if you look at the coefficient of t to the power, we are getting f of r into a naught. Coefficient of t to the power 1 plus r is given as f of 1 plus r into a1. Similarly, look at the coefficient of t to the power r plus n. So, coefficient of t to the power n plus r is this quantity, which is nothing but f of n plus r a n, and here we have this summation a n minus 2. So, this is your coefficient of t to the power n plus r, that is what we are writing here. So, here we are writing f of n plus r a n equal to n plus r whole square minus p square a n equal to minus of a n minus 2, and here we are writing this as n greater than or equal to 2 here. So, here we are getting these 3. So, this is corresponding to t to the power r, this is corresponding to t to the power r plus 1, this is corresponding to t to the power r plus n. So, first equation will give you the possible values of r for which we must have which will for which we will get a solution here. So, from equation 1, our which is known as initial equation. So, here this will give the value of r. So, if you look at the values of r will be r1 equal to p and r2 equal to minus p square. So, it is r square minus p square is equal to 0. So, it is r plus minus p. So, r1 we are getting the p and r2 equal to minus p, provided that p is greater than 0, this we are assuming. So, now we here we are assuming that p is greater than 0 and 2p is not equal to 1. It means that difference is not an integer here. So, here we are assuming that p is positive and 2p is not equal to 1 here. So, here let us find out, once we have the values of r1 and r2, then we our next aim is to find out the coefficients. So, let us find out the case that r1 equal to p. First we look at the r1 equal to p and find out the coefficient, and then look at the case r2 equal to minus p, and then again we find out the coefficient. So, let us look at r1 equal to p. Then when r1 equal to p, then the first equation will give you that a naught is non-zero. So, we cannot calculate a naught value here, and then but when r equal to p, we can easily calculate using this formula to find out a1. So, from here we can find out the value of r1 here, a1 here. So, from this if you put r as p, then it is 1 plus p whole square minus p square into a1 equal to 0. Now, since this term is non-zero, so a1 has to be 0. So, here we can say that this equations 2 forces a1 to be 0, and if you look at the recurrence relation, that is this will give you the values of an in terms of an minus 2. So, you can write an as minus an minus 2 divided by n plus r whole square minus p square, that is this expression is valid for n greater than or equal to 2, and in this case your r is equal to p. So, an is given as minus an minus 2 divided by p plus r square minus p square, and we can observe here, since a naught is non-zero and a1 is equal to 0. So, using this expression we can write that a3, which is given in terms of a1, it has to be 0. Similarly, all the odd coefficient has to be 0 here. So, we can say that since a1 is equal to 0, so all odd coefficients are 0 because of this recurrence relation. So, we need to find out only a2 in terms of a naught. So, using a2, a2 is equal to minus n equal to 2. So, minus a naught divided by 2 plus r is p here, 2 plus p whole square minus p square, that we are writing here, that 2 square 1 plus p a naught, we are taking out 2 out, right. So, let me write it here, an is what, a of 2n I am writing, that is a minus a of 2n minus 2 divided by 2n plus p whole square minus p square, right. Or we can simplify this further, an 2n minus 2, and here we can write 2n plus p minus p. So, that is 2n into 2n plus p, and this is valid when n equal to 1, 2 and so on. So, here I am writing that in place of n, if we write 2n, then we can consider this, and if you simplify this further, then what is a2n? a2n is going to be minus a of 2n minus 2, and 2 we can take it out, 2 square n into n plus p you will get. So, that is what we are using here. So, a2 is minus a naught divided by 2 square 1 plus p into a naught. Similarly, you can calculate a4 using A2. So, A4 is minus A2 upon 2 square to 2 plus p, and if you put the value of A2, then it is 1 upon 2 to the power 4 factorial to 1 plus p into A naught, and so on. So, in this way we can find out all the even coefficient. So, once we have even coefficient, we can write that our expression is like this: A2n is equal to minus 1 to power n 2 to power 2n factorial n 1 plus p 2 plus p up to n plus p. So, once we have A2n, then we can write down our solution as y1t A naught, here A naught is missing, A naught summation n equal to 0 to infinity minus 1 to power n. We are writing this expression, that is 2 to power 2n factorial n 1 plus p 2 plus p up to n plus p, and y to power this r plus 2n plus r. So, 2n and r is p here. So, it is y1t is given as this. So, if for simplicity, if we take A naught as 1 upon 2 to the power p upon factorial p plus 1, we will see why we are choosing this value. We will discuss later on. So, when we choose this value A naught equal to 1 upon 2 to the power p gamma p plus 1, then this expression will take a simpler form, that is here if we take A naught as this thing, it means that here it is minus 1 to power n divided by 2 to power 2n factorial n 1 plus p up to n plus p into A naught value is 2 to power p and factorial p, you can write it here, and y to power 2n plus p, and summation n equal to 0 to infinity. So, we can simplify this as minus 1 to power n as it is, factorial n as it is, and this we can write as gamma n plus p plus 1 here, and here this y to power 2n plus p is here, and here also we have 2 to power 2n plus p. So, we can write y by 2 power 2n plus p, and we using this special value of A naught, this will represent a series expansion and which we call as JPY, and this is known as Bessel's function of order p of first kind. So, here using the value of A naught as this, we have expression for JPY given as this: n equal to 0 to infinity minus 1 to power n divided by factorial n gamma n plus p plus 1 y by 2 to power 2n plus p. So, this is the expression for Bessel's function of order p, and this value A naught which we have taken is we can obtain using orthogonal property of Bessel's function. So, when we study this Bessel's function of order p, there you can understand how to find out this A naught value. Since it is valid for any A naught, so in particular if we take A naught as this value, then this will take a simpler form, and which we are writing as Bessel's function of order p. Now, look at the other solution corresponding to R2 equal to minus p. So, we will get the other solution, but before that let us summarize this, that when p equal to k, then 16 becomes jky as summation k equal to n equal to 0 to infinity minus 1 to power n factorial n divided by factorial n into n plus k factorial y by 2 to power 2n plus k. Please remember here we are writing k as integer value, but this value, this expression is valid for any real p such that p is greater than 0 and 2p is not equal to 1. So, this expression is valid for any p, whether it is integer or non-integer, but if p is an integer, then this gamma n plus p plus 1 is reduced to factorial n plus p, that is what is written here. So, this is expression of Bessel's function of order k, and it is written like this. Now, find out the second solution. So, here replace p by minus p. In 16 we get j of minus py equal to n equal to 0 to infinity minus 1 to power n factorial n divide factorial n gamma n minus p plus 1 y by 2 to power 2n minus p. So, here if you look at this is quite symmetric. The only thing is that here we have just replaced p by minus p. You can check that actually we are getting this thing. So, this is I can say that it is homework, that the other solution corresponding to R2 equal to minus p, we will get the following expression. So, here we say that when p equal to k, then 17 becomes this, and this is known as Bessel's function of order minus p, or Bessel's second solution. Okay. Now, as we have discussed earlier that the method of Frobenius may not be able to find the general solution of the differential equation in following two cases. So, when R1 equal to R2, then we may not find out two Frobenius series solution method. It means that of course, one series solution will be given, but the other two may not be of the Frobenius series form. Similarly, when R1 minus R2 is a positive integer, here also we have a possibility that one solution is given in terms of series, but other solution may not be given in Frobenius series solution form. So, let us consider these cases. So, first let us consider the equality case, that when R1 is equal to R2, and in this case we have only one solution of this form, that is y1 t equal to t to the power r1 n equal to 0 to infinity a n t to the power n. We are not able to find out the second series solution. So, the only thing we know is that whatever second series solution whatever second solution exists must be linearly independent to this, and here we say that second linearly independent solution is given by y2 t equal to y1 t ln t plus t to the power r1 n equal to 0 to infinity b n t to the power n, where b n n greater than equal to 0 are constant to be find out. So, here if you remember the case of Cauchy-Euler equation, in Cauchy-Euler equation if we have a case of equal roots, then we know that solution is given in terms of y1 t ln t plus y1 t ln t. So, in this if you look at this solution second solution y2 t, here this ln mod t makes the second solution a singular solution in near t equal to 0, and most of the times we are not able to utilize in a full swing. We say that and to find out second solution we adopt the method similar to the method used in finding a second solution of Cauchy-Euler's equation that we are going to find out. So, let us rewrite our equation 31 in the form that y1 t comma r is given as n equal to 0 to infinity a n t to the power n plus r, to emphasize that the solution y t depend in our choice of r. So, here of course, the solution is depending on r. So, when you take r equal to r1 we have a solution, when we take r equal to r2 we have another solution, but in this case you write y1 t t comma r as this n equal to 0 to infinity a n t to the power n plus r. Now, using this our expression is written as L of y t plus r equal to a naught f t t to the power r plus n equal to 1 to infinity a n r f n plus r plus k equal to 0 to n minus 1 k plus r p n minus k plus q n minus k a k t to the power n plus r. So, that is the simplification of the basis the differential equation when you put y t r as a possible case of solution. So, we need to find out the possibilities of this r and the coefficient in a way such that this expression is coming out to be 0. So, we need to find out r and a n in a way such that this expression is gives out to be 0 value. So, here we have to choose a and r as 12, requiring that the coefficient of t to the power n plus r be 0. So, it means that a n plus r is given like this. So, this is the expression which we have already utilized, that f n plus r into a n r is given as k equal to 0 to n minus 1 k plus r p n minus k plus q n minus k a k r. So, that is how we choose our coefficient a n's. So, when we choose this coefficient a n like this, then your this L y is simplified like a naught f t into t to the power r, because we have taken our a n in a way such that this expression is going to be 0. So, choosing n in a way such that this expression is 0, then what we left is L of y t r is equal to a naught f t t r f r t r. So, there is a small correction here that it is f r t r. So, once we have made this choice, then we have L of y t r as equal to a naught f of r into t to the power r. Now, we know that in case of equal root f of r is given as r minus r 1 whole square. So, it means that I can write our previous equation as L of y t r equal to a naught r minus r 1 square t to the power r. Now, again we already know that when y is equal to y 1 t, then we have a 0 of this. So, it means that for r equal to r 1 we already have a solution. So, it means that L of y t r equal to 0, and then we have a solution y1 t equal to t to the power r1 summation a naught plus summation n equal to 1 to infinity a n r1 t to the power n. So, that we already know. So, one solution is given by this. To find out the other solution, we already know that let us differentiate this equation corresponding to r with respect to r. So, apply divided by divided r of L of y dr equal to L divided by divided r of dr. So, here we already discussed that L is a differential operator in terms of t. So, if we apply differential operator corresponding to r, it will go inside. So, here we write L divided by divided r of dr. So, if you differentiate divided by divided r, it is a naught divided by divided r minus r1 square t to the power, because in right hand side we have this. So, here we have L divided by divided r of ty is equal to a naught 2 r minus r1 t to the power plus r minus r1 square ln t to the power. And if you put r equal to r1, then right hand side is equal to 0. So, it means that divided by divided r at r equal to r1 will give you a second solution. So, how to find out second solution? So, divided by divided r at r equal to r1 is also a solution. So, it means that y2 t, which is given as divided by divided r of y, y1 is already given n equal to 0 to infinity a n r t to the power n plus r at r equal to r1 will also give a solution. So, simplify this expression. So, what you will get n equal to 0 to infinity. Now, a n is also depending on r. So, here when you differentiate this, you will get what? A n r1 t to the power n plus r1 ln t. Here I am just differentiating this t to the power n plus r. So, here we are getting t to the power n plus r1 ln t, and then differentiate this a n r. So, we get n equal to 0 to infinity a n dash r1 t to the power n plus r. So, here what you will get? This you write as n equal to 0 to infinity. So, a n r t to the power n you are taking out and differentiating t to the power r. So, differentiating t to the power r means t to the power r ln t plus summation n equal to 0 to infinity t to the power n plus r as it is, then differentiate a n, that is a n dash r. So, that is what we are writing here. So, we can write this as here if you simplify, what is this? If you look at this is what? A n r1 t to the power n plus r1. If you look at this, then this is nothing but y1. So, this the first term is written as y1 ln t, and second term is written as n equal to 0 to infinity a n dash r1 t to the power n plus r. So, it means that the b n is nothing but a n dash r1. So, it means that here second solution is given by y1 ln t plus n equal to 0 to infinity and a n dash r1 t to the power n plus 1 n plus r, and here this we are able to get because we have already discussed the similar case in case of Cauchy-Euler equation. So, here we have seen that one solution if is given by y1 t, then another solution is given by y2 t as divided by divided r1 divided by divided r equal to r1, and it is having this expression y2 t equal to y1 ln t plus n equal to 0 to infinity a n dash r1 into t to the power n plus r. So, as claimed, this is having the form which we have already claimed. The only thing is that b n is now replaced by a n dash r. So, here I will stop here, and we say that in case of equal roots, we are not able to find out both the solution as Frobenius series solution method, Frobenius series solution form. So, one solution is given in terms of Frobenius series solution, but the other solution is not the Frobenius series solution form. So, in equal roots we have second solution given by y2 t, and general solution we can find out using y1 and y2, and in next class we will discuss an example based on this and the other case, that is when r1 and r2 differ by an integer. So, in next class we will continue this lecture. Thank you very much for listening us.